All right, students, another solution here. I'm getting some questions on number 45, and I think rightfully so here because there's a little trick that the author could be a little more clear both in the problem and in the textbook, and one that is true. It takes a little bit of proof, and I'm glad he touches on it in the textbook, but the little trick, if you will, is his hint. And so let me point out something. If you have two objects that collide, so in this case we're going to have two identical pucks collide on an air hockey table. So we have something like this. First one comes along, side swipes the first one, and ricochets off. And so this problem says two identical pucks collide on an air hockey table. One puck is originally at rest. So I'll put this one, the one that's originally at rest. So it's just sitting there when the one coming along sideswipes it. It says if the incoming puck has a speed of 6 meters per second and scatters off at an angle of 30 degrees, what is the velocity, the magnitude, and direction of the second one? And there's where your author could be a little more clear. He does not actually say that this is an elastic collision. But in the textbook and in the hint he's given here, he says, go ahead, and it says, you may use the result that the angle of between the first and the second is 90 degrees here. Now, that is true only in the special case of, and there's a bunch of conditions. The first condition is one of them must be at rest. Okay, well, we have that. The second condition is they must be of the same mass. Okay, they say that. They say they're identical mass. The other condition, and the most important one, is that the collision is elastic, and so the kinetic energy is conserved. And so if those conditions are all met, then there will be a 90-degree angle between the one coming in and the one going out. And he says go ahead and use the condition of 90 degrees. And I'm a little bothered by it because he doesn't really say it's true, but he does say you may use the result that it equals 90 degrees for elastic collisions of objects that have identical mass. And he should have added one that is stationary. So he helps us out by saying we can use it, but I think he should have put in the question that it was elastic, not in the hint. Okay, so anyways, maybe I'm just splitting hairs there, but if that was any of your issues or your problems, knowing it's elastic, it does say that down in the hint. But I think the biggest problem students might face in this one is just knowing the special case that was worked out, that this would be 90 degrees. So by the author giving this as 30, they've also given this as 60, okay? So then we can apply our conservation of momentum, and we can say the initial momentum in the x direction is equal to the final momentum in the x direction. And maybe a little down on my page, I'll say, and the initial momentum in the y direction has to equal the final momentum in the y direction. And then hopefully what I will have then is my two equations with two unknowns, and I won't even necessarily need to work out the conservation of energy issue. Like I said, that information from conservation of energy allows me to get the 60 degrees. So I've pretty much already did right here the feature that says the initial kinetic energy is equal to the final kinetic energy. And so that's the condition that gave me the 60. So without writing it out in an equation and without going through the proof as your author did, I would say I've got three pieces of information. elastic collision, which has got me the 60 degrees, so that's already used up. But then I'm going to have the x and y component of this thing. And so that'd be my two unknowns. Watch, I'll go through. So before the collision, okay, I have the mass of the one moving, and it's moving with a velocity of 6. And then I have the momentum in the x direction of the second one. Now remember, the second one's not moving, so that's going to be a 0. Then, of course, it hits, and so when it hits this one, they just say it's 30 degrees. So if I call this V1, what I can do is say it's m times V1 times cosine of 30 degrees. And again, I'll just say the mv because that's the momentum, but the cosine of 30 because I'm looking for the x component adjacent to the 30 degrees. And then if I also now have the second one moving, so this is after the collision. Before the collision, it was 0 motion. But now after the collision, it's moving. It would be an m and a v2, calling this velocity v2, and then it would be cosine of 60 degrees. And fortunately, there's an m in each case that's going to cancel off, because otherwise it would look like there might be 3 unknowns in this equation. So simplifying the left-hand side, I just get the number 6. Putting in cosine of 30, which would be 0.866 V1, and cosine of 60, which is a half, I get what I would call my first equation of a system of equations. And that's what we're looking for, these two velocities, V1 and V2. I'll just read the question. What does it say here? A, if the incoming puck has a speed of 60 and scatters at 30 degrees, what is the velocity of the struck puck? Oh, so I guess we're really only looking for number 2. But, okay. But we got to somehow have an equation that, has a second piece to it, because I've got 2 unknowns here. And I just wanted to confirm, cosine 30 is that root 3 over 2. Okay, good. And cosine of 60 is 1/2. Okay, so that's what I said they were. All right, so now let's try the y direction. Now in the y direction, we've got 0 plus 0 before the collision. You see the first puck is moving, but it's all x, so it has no momentum in the y. And the second one's not even moving, so it has no momentum in either x or y. So that's why I put a 0 there and a 0 there. And of course, then after the collision, number 1's going up, so I'd say it is mv1 sine of 30 degrees. And then the other one is kind of heading down. Now it's right and down, so the right made me use a plus sign for the x momentum. But for the vertical momentum, I'm going to put a minus mv2 sine 60 degrees. And again, same thing can be said. Luckily, I can solve this because they have the same mass, and I can cancel them off out of every term. And I could even move this over to here. And then sine of 60, which would be the same as cosine of 30, would be the 0.866 V2. And I'll make it a positive when I move it to this side. The sine of 30 is 1/2 of V1. And now I would say I have my second system of equation. So using the principle of conservation of momentum, but twice, one for the x direction, one from the y direction, I've got a system of 2 equations that has the 2 unknowns, V1, V2, and V1 and V2. So maybe the easiest way to do this is to remember I'm trying to find V2. So why don't we solve this for V1 and put it into here. That'll eliminate V1, and I'll have an equation which only has V2. So here's V1. I'm going to divide by a half. That would get rid of it, and it would make that one twice as big. So let's see. Double an 8 is a 16, 1, 6, but doubling that's going to 12. I'm going to bring that over 2, but that 2 is going to become a 3, and that's a 2. I think I did that right. 12, carry 1, 12, 13, carry 1, 16, 17. Yeah. All right. So based on these numbers, whatever the speed of the number 2, the struck one, if you increase it by the 73%, so 1.73, increase it by 73.2%, you're going to get speed number 1. So I'm going to use this and put it into my first equation. So in place of V1, I'll put 1.732 V2. And then, of course, plus 1/2 of V2. All right, so grabbing my calculator here, I'll put this number right there and multiply it by 1.732. And so that's about 1.5. Okay. Yeah, that would make sense. It's square root of 3 times square root of 3, which is a 3, and then a 3 divided by a 2 is 1.5. Okay, so that's 1.5. And now I'm going to then add another half and get a 2. So 2 V2. And so V2 would equal to a 3. Okay. And that's all I have to do for A, because A is all they asked for. Let me just double check. A says the incoming puck is, what does it say? Somewhere scatters. The incoming puck has a speed of it scatters at. Yeah. What is the velocity, magnitude, and direction of the second puck? So the second puck has a direction of 60 degrees from the line of the original action and has a speed of 3. Now, I can use that right here to say what is the speed of number 1. Because taking that speed of 2 and multiplying it by 1.732, I get a speed of my bad. That was not what I had in my calculator. I had the number 2. I was thinking I had the number 3 in my calculator, but I guess I just did that math in my head. All right, let me try this again. So speed of 3 times, so number 2 is speed of 3, times 1.732 comes up with a speed of number 1 of 5.196 meters per second. So coming back up here, remember the first one when it came in was going at 6. So it brushed it sideways and ended up slowing down a little bit. Changed direction also. But it slowed down from a 6 down to a 5.196. And of course, the other one sped up from 0 up to 3. Okay. Now, the reason I bothered to calculate those, because I was looking ahead here at B. B says confirm this is elastic. So let's figure out how much kinetic energy do you have before the collision. And we don't know the mass, but we know its speed is a 6. 6 squared is 36. Half of that is 18. And so we can't get a number, but we can say it's 18m. And so whatever m is would then, if we knew it, we could actually get a number for the energy. Now, after the collision, we'll have a 1/2 m. And remember, number 1 is still moving at 5.196 squared. And number 2 is now moving with a speed of 3. And since I can do this in my head, 3 squared is 9, half of 9 is 4.5 m. And then this one would be that speed squared and then half of it. And so this is 13.5 m. And if you add them together, 13 and 14 is 17, and a half make 18 m. So sure enough, the speeds we've gotten out of this, because we assumed 60 degrees, which would only be true if the energy was conserved, means that it's kind of a circle reasoning that we would come back and say, hey, energy is conserved. I mean, to be 60 degrees, energy, kinetic energy, has to be conserved. So to come back and say energy is conserved is just saying what we assumed at the beginning. So it's I wouldn't say this is a proof it was elastic. We said it'll be 60 degrees, and this is more of a proof that if it was 60, so the whole thing between them is 90, this is proof that that's the case you get for the elastic collision. All right, well, hope all that helps. All right, take care.